Okay, let's see 5.1 eigenvectors and eigenvalues. Um, Let me start with introducing definition of eigenvalues and eigenvectors. Definitions. Okay, so here. An eigenvalue eigenvector, sorry, of n by n matrix, matrix A. This is n by n matrix. Okay, this is an non-zero vector. Dx. Okay. Such that A times x is equal to lambda x. Okay. And for the scalar lambda, okay, that lambda is called the eigenvalue. So this is lambda is called eigenvalue of A, which is A. Okay. So now you see that the AX bar is equal to lambda x. Then how can you find the matrix, I mean, the eigenvalue and eigenvector? Okay, so then we need to solve the equation for, the x bar. I mean, we assume that lambda is given. Then how can you find out x bar? Then we move lambda x bar to the left-hand side. X bar minus lambda x bar is equal to definitely zero vector. Right? But we can combine this, the left-hand side, to like this, ax bar minus lambda x bar is nothing but lambda times identity matrix, right? In the x bar. Why we have to do this? Because we need to match the size of the first term and the second term. Ax bar is the I mean, to take out x bar, we need to make rewrite lambda as a matrix. That's why I add the identity matrix. It's n by n identity matrix. This is n by n. Okay. Okay. And then okay, so then this is equal to a minus lambda I, because we can take out x bar, okay, now, finally. Because without, the multiply by, without the identity matrix, we can't just take out x bar because a minus lambda, it doesn't make sense. A is a matrix, lambda is a scalar. How can you possibly subtract the scalar from the matrix? That's why we need put identity matrix. Okay. Okay. So now we got this. A minus lambda I times x bar is equal to 0. Okay. So I want to figure out whether or not, I mean, if there is a non-trivial solution. Okay. Think about this. Solving this one, then we can expect that, we can expect two cases. This is a matrix equation, right? That matrix equation has a trivial solution, which means the x bar equals 0, or non-trivial solution, right? But we are not interested in this trivial solution because, see, definition of eigenvector, non-zero vector. Eigenvector must be non-zero vector. So in what circumstance this matrix equation has non-zero vector, which means the non-zero non-trivial solution? In what circumstance? What circumstance? Lambda is what? Lambda is an eigenvalue. of matrix A if and only if what A minus lambda I x bar equals 0, that equation has what a non-trivial solution. And then it means that what A minus lambda I is, this is a matrix, right? Is not invertible, isn't it? If A minus lambda I is invertible, then what? Then there exists, okay, there exists inverse matrix of A minus lambda I, that we do multiply, left multiplication of inverse of this guy on both sides, then X bar turns out to be 0 vector. So there, that means, you know, what this, the matrix equation doesn't have non-trivial solution. It means that there is no eigenvalue eigenvector. So in order to have eigenvalue eigenvector, A minus lambda I must not be a invertible. Okay, not invertible. There does not exist. Okay. Okay, it's not invertible. That, what does that mean? It means that, you know, I can keep going, you know, I can write so many, you know, equivalent statement. The null space of what? A minus lambda I is not just what? 0 vector, right? Okay. And so on, figure out how to solve. Okay. So, and let's say put first one and second one. This, the set of all solutions um to this one. Let me put this one is 3, equation number 3. What? That's the just a null space, right? This is just a null space of matrix A minus lambda. Okay. All right. So then this space is called the set of all solutions. It's called the eigenspace. Okay. So assuming that, you know, A what here we assume that A is a n by n matrix, right? So this is the A minus lambda is also n by n matrix, right? So this is n by n, right? And the X bar is what? N by 1 column vector, right? And the eigenspace is a set, the set of all solutions, I mean X bar, okay? That eigenspace is a subspace. This is eigenspace, and the eigenspace is the subspace, a subspace of what? Rn. Okay, Rn. Okay. And then this, the eigenspace, what? This consists of all solutions, right? X bar and including 0, right? Okay. So this example. But A, let's say matrix A 1, 6, and 5, 2 is given. Okay. And then let's say lambda is 7, eigenvalue is given. Okay. Let's find the corresponding eigenvectors. Okay. Find the corresponding eigenvectors. How can I find out? Okay, so to find out corresponding eigenvectors in this problem, we gotta solve that homogeneous system, right? So let's just assume that lambda equals 7 is a really eigenvalue. Then when you solve that homogeneous system, you have to get free variable, get non-pivot column, I mean. Okay, otherwise 7 is not gonna be eigenvalue. All right, so let me just do reduce row reduce the augmented matrix. Okay, so A minus lambda I gonna be -6 and 6 and 5 and -5. Now I put 0 column vector. This is a column vector on the right hand side. Okay, so this is augmented matrix. And then we're gonna get using the elementary row operations, we're gonna get EF. Okay, so 1, -1, 0, and a 0, 0, and 0. Okay. So you see, uh, 1, that's the pivot column, pivot position. So this is a pivot column, right? So that's the non-pivot column. All right. So what it means that what? Look at the first row, which is equivalent to that equation, x1 minus x2 equals 0, right? It means that x1 is equal to x2. Right? So then x bar eigenvector, I mean solution column, solution vector of that homogeneous system, say x1 and x2, is gonna be what? Just I don't know, maybe we can say x2 times 1, come on, 1. You can say that, right? Yeah. Because x1 is the free variable, sorry, basic variable. This is a free variable. Okay, so normally we express a basic variable in terms of free variable. That's why I put the x2 right here. Okay. So how many, eigenvectors in here? There are infinitely many eigenvectors, right? Is it? So for any the vector having the form constant times 1, which means that in a R2 space, so 1, 1 is this, right? That's the 1 and 1. Let me use the column vector notation, 1 and 1 right here. Then any vectors along that line, any vector along this line must be a eigenvector corresponding to eigenvalue 7. What does that mean? But AX bar, I mean, so AX bar for this eigenvalue 7, then AX bar can be represented by just line. Okay, you see, corresponding to eigenvalue 7, actually. Okay, so here's a 1, 1, and then here's a 7, 7. Maybe here's 7, 7 right here. 7, 7. Okay. So what does that mean? Give me a second. A times the for example 7, 7. This is equal to nothing but 7 times 1, 1. You see? So now we can see clearly, we can see that how what's the role of the matrix A? Oh, this is 1, 1, sorry. Here's 1, 1. I'm sorry. Okay. So matrix A times and 2, 2 is equal to what? Oh, give me a second. This is 1 x4. Yeah, this is 7, 7, right? X2, 7, and 7. Hold on a second. I got confused. x4, x2, 7, okay, and then 7, 7. This is 7 times 7, 7. Oh, yeah. So there is a 49, 49. There is a 49, 49 for this matrix, for this vector. Okay. So matrix A times this eigenvector 7, 7 is equal to lambda 7 times 7, 7. Yeah. So this is an eigenvector. Okay. That's the eigenvalue. Okay. All right. So, well, not only 7, but other maybe, yeah, you can pick any eigenvector. Then the matrix A times that eigenvector must be equal to 7 times that eigenvector. That's the meaning. So that we can see the role of the matrix A. Okay, so let's see other examples for but let me keep it. I mean, okay, let me just briefly go over exam 4 in textbook. So matrix A is given by 4 and negative 1 and 6 and 2, 1, 6 and 2, negative 1, 8. Okay. And let's find the eigenvalue corresponding to find the eigenvector corresponding to eigenvalue 2. Okay, let's say lambda is 2. Okay. So then we do this. A minus lambda 2 x bar is equal to 0. We just set the homogeneous system, right? Lambda actually 2 times the matrix, identity matrix. Okay. So what's this? This is going to be 4 minus 2, right? 2 minus 1 and 6. The 2 minus 1, 6, and the 2 minus 1, 6. 3 rows are identical. Interesting. Okay. Yeah, definitely there is 0 right here. Okay, this is 0, 0, and 0. Augmented matrix. Okay, so since 3 rows are identical, definitely we're gonna get just first non-zero row. Other rows will be 0, right? Because I just use the replacement, elementary operations, and it's easy to get this, right? Okay, so what does that mean? That means that 2x1 minus x2 and a plus 6x3 equals 0, right? So which one is a bit basic in the other three? So that's the basic, right? Basic variable. These two columns are free, right? So it means that we express x1 in terms of x2 and x3. So eigenvector x gonna be x1 and x2 and x3 gonna be 2 times, is it? It's gonna be what? X1 is here, and the x1 is what? X2 minus the 6 times x3, right? 1/2, I'm sorry. 1/2 and x2 minus 6 times x3. And then here x2 and x3. You see? So that is equal to what? 1/2 and then x2 times, sorry, 1/2 and 1 and 0, right? And then minus plus x3 minus 3, 0 and 1. So what does that mean? It means that what? This is general solution, right? So eigenvector will be generated by 2 column vectors. It means that eigenspace must be span of these 2 vectors, isn't it? Right? So eigenspace is equal to span what? Of what? This one. Oh, well, this 1/2 and then 1 and 0. Okay, and then -3 and 0, and like this. Okay, so yeah, okay, so eigenspace is this. Mm, but look at the two vectors. Has a 3 entry. For each vector has 3 entry. So these two vectors must be on 3-dimensional space, but these two vectors will generate not 3-dimensional space, but R2 is plane, right? So here's x1, x2, x3. Okay. So let's say, I don't know, maybe. Let's say this is a plane. Give me a second. Okay. So, for example, okay, so let's say this is the V1, this is V2. Let's say this is V1, this is V2. Then the plane is a plane generated by V and V2, which is eigenspace. Okay, you see right there. And then we multiply by A, okay, A times A X bar, and the X bar is on the this plane, eigenspace. Okay, this is eigenspace. Corresponding to lambda equals 2, or lambda equals 2. And then I just pick the arbitrary vector on the eigenspace plane, I mean. So then AX bar will what? X1, X2, X3. What happened? Anyone can tell what what's gonna happen? X3. Well, this is equal to what? Since the X bar is on the eigenspace, we know that AX bar is equal to what? 2 times X bar. So X bar will be elongated by 2, factor of 2. Like this. There's 2 X bar. So that X bar is transformed by 2 X bar stretched out by a factor of 2 by this one, matrix A. Now you see that clearly how the matrix A works if we multiply the matrix by a vector on the eigenspace. Okay. We're on the same plane right here. Okay. You got it? That's the meaning of the eigenvalue and eigenvectors. So by finding eigenvalue and eigenspace, we can simplify or clearly understand the matrix, the role of the matrix A. Okay. Here's a theorem 1. Okay, we just see the examples. Okay, and then let's see example 1, 5.1. The eigenvalue of a triangular matrix are what? The entry on its main diagonal. Okay. So the eigenvalues of a triangular matrix are the entry on its main diagonal. Let me prove it. What does that mean? Okay, so what's a triangular matrix? There are 2 types of triangular matrix, right? Upper triangular matrix, lower triangular matrix. Let's pick the one of them without loss of generality. So okay, right here is non-zero here and is 0 here. Okay. The eigenvalue of that triangular matrix are what? These. The entry on the diagonal, on the main diagonal. These are eigenvalues. That's what theorem says. How come? Yeah, we start with the a minus lambda I. Okay. So and then matrix A. Let's say. Okay, let me set the matrix A is this A11, A22 through the A and let's just A33. Okay, let's think about 3 by 3 matrix. Here's a 0. Okay, the A12, A13, right? The A23. Okay, 3 by 3 matrix. So then we just easy to catch up. Then A minus lambda I gonna be what? A11 minus lambda, right? And the A12, A13, and the A22 minus lambda, the A23, and the A33 minus lambda, is it? They're all 0. This is A minus lambda is equal to 0. I mean, x bar is x bar here, and then x1, x2, and x3 is equal to what? 0, 0 vector, right? 0, 0, 0. Okay, but think about this. I mean, in order to have a non-zero vector, in order to have a non-zero, non-trivial solution, what? And this the one of column vector must be non-pivot column, isn't it? If all 3 columns are pivot column, this system gonna have only trivial solution. It means that there is no eigenvalue. So in order to have non-trivial solutions, for instance, the third column must be non-pivot column, which means the A33 minus lambda must be 0, which means the lambda must be A33. Is it? Let's say second column is non-pivot column, which means the lambda must be A22. Or lambda must be A1. That's why is eigenvalues of triangular matrix are the entry on its main diagonal. So eigenvalue must be A11 or A22 or A33. Otherwise, this system not gonna have a non-trivial solution, right? This makes sense, right? So okay, how can I? So the scalar lambda, right, is an eigenvalue for matrix A, if and only if what? A minus lambda I, right? X4 is equal to that homogeneous system has a non-trivial solution. A non-trivial solution. Okay. So that means what? If and only if the equation has free variable. The homogeneous system, right, has a free variable. If and only if free variable. Oh, okay. It means that what? A11 minus lambda equals 0. A22 minus lambda equals 0. Or A33 minus lambda equals 0. Okay. That's it. Done. Theorem 2. So if you got the triangular matrix, then it's easy to find out eigenvalue. Okay. So now you see that that's why. Oh, okay. How can you make a matrix A to diagonal matrix? What triangular matrix? Do you remember that Elliott factorization or echelon form, Gaussian elimination? So if you got matrix, if you want to find out eigenvalue, then decompose matrix A to echelon form. Then so that we can get the then so that we can rewrite we could convert rewrite the matrix A to the triangular matrix. Then we can figure out the eigenvalue easily, right? So theorem 2, if V1 to the V and R, these are vectors, column vectors, eigenvectors. Correspond to distinct eigenvalues. That's V. Lambda 1 to the lambda R. This is R, okay? R, not N. R, okay. Of an M by N matrix. Okay. Then the V1 through VR. 1 through VR. This is a linearly independent. Okay, here's a proof. Okay, well, okay, let's figure out what theorem says. V1 through VR are eigenvectors corresponding to distinct eigenvalues, V1 through the VR. Then V1 through VR is linearly independent. Okay, can you say that then the V1 through VR? Okay, so what's the relationship between the matrix A and then this one? Let's figure out. Okay. Anyway, we can clearly see that this is linearly independent, isn't it? Because these are eigenvectors to distinct, corresponding to distinct eigenvectors. It means that we can express a vector, eigenvector, in terms of a vector as a linear combination of other eigenvectors, because these are eigenvectors. I mean, lambda 1 to lambda R are distinct eigenvectors. Eigenvalues, right? Eigenvalue. Sorry, eigenvalues. Let's see, proof. Okay, suppose what you're gonna do. Okay, so suppose that lambda 1 to lambda R is linearly dependent. And then we're gonna we get the end up with a contradiction. 1 to the lambda R, VR is linearly dependent. Okay, it's dependent. All right. This is dependent, which means that say VP can be expressed as the I mean is I goes P plus 1, okay? I goes 1 through the P and then a CI and a VP, isn't it? BI. We can express that because this is linearly dependent. Okay. So it means that a vector in this set can be expressed as a linear combination of preceding vectors. That's the by the theorem 1.7 theorem 7. Theorem 7 in section 1.7. Yeah, okay, let's look at this. So let P be the here P, okay, is this P? So right there, and P be the least index such that BP plus 1 is a linear combination. I mean this, I goes 1 through the P, and then CI, VI. Okay. So up to P, these are the V1 through the BP are linearly independent. Now BP plus 1 can be expressed as a linear combination of preceding vectors, like this. Okay, let's assume that. So now then, what happens? Okay, so then there exists. There exists. You see the C, there is CI, right? Scale CI, there is such that there exists C1 through the CP such that what? Sigma, and then I mean BP plus 1 is equal to sigma. I just repeat this this expression. Okay, you don't have to repeat this. Okay. Okay, so this is just optional. Okay, you don't have to mention this. That expression include that meaning. So you don't have to write this line. Okay, just optional. Then what are you gonna do? We're gonna do some trick, apply some trick. So multiply this one, this one here, okay, this one by the by matrix A, okay. So matrix A from here. Okay, let me say this is equation maybe 5, okay. So multiply, okay, both sides. Equation 5 by matrix A. And what? A, then we're going to get A and then P plus 1 is equal to the sigma I goes 1 through the P, and then Ci and then A times Vi, right? Well, you know what? What's this? This is equal to what? Lambda P plus 1, right? And then VPI. And then this one is what? Is equal to what? Ci times lambda I and then Vi, this. Oh, right? Okay. So let me extend this expression. So it means that what? C1 and then lambda 1 and V1 plus C, through the CP and then lambda P and then VP is equal to what? Lambda P plus 1 and then VP plus 1. That's what that says, right? Right. And now then, 1. Then we multiply, instead of that, we multiply the both side by lambda P plus 1. 5 by lambda P plus 1. Okay. Then what? We're gonna get lambda P plus 1 plus VP plus 1, right? Is equal to sigma, and then I goes 1 through the P, and then Ci lambda P plus 1, and then Vi. Okay, so now we got this, and then this. Now we subtract this one from that. Okay, so let's say this is equation 6. Let's say this is equation 7. We subtract the 7 from 6. The left-hand side going to be 0, right? So, 6 minus 7, 7. Then we're going to get a 0 vector, right? 0 vector is equal to, right? Is equal to what? C1 times lambda P, lambda 1 minus lambda P plus 1. And then V1 plus C2 and then lambda 2 minus VP plus 1. V2. Through the what? CT, right? And then lambda P minus lambda P plus 1. And VP plus 1. Ooh. BP, right? Okay. But you know what? We assume that what? V1 through BP are linearly independent. Since V1 through the BP is linearly independent set. Is A. Okay. Let's say. What does that mean? It means that what? C1 and lambda 1 minus lambda p plus 1 through the CP and the lambda p minus lambda p plus 1. It must be 0. But you know what? Lambda 1 to lambda p plus 1 distinct. So this is not equal 0, right? That is not equal 0. And this one is not equal 0. So it means that what? Since here, then what? Since lambda 1 through the lambda p plus 1, I mean, lambda, not only lambda p plus 1, up to lambda r are distinct. Distinct, it means that what? C1 through D1, CP must be 0. This is equal to C2 is equal to through D1, CP equals 0. That's a contradiction. What's this contradiction? Why? Hmm? Well, what, at which, okay, why we got the contradiction? This is a contradiction. Why? So this is a contradiction. Why? Because if C1, C2 up to the CP are 0, it means that back to equation 5, V sub P plus 1, this Eigenvector turns out to be 0. That's a contradiction. Why? In this theorem, we assume that V1 to Vr are eigenvectors, which means that these vectors must be non-zero vectors. But we got 0 vectors. That's a contradiction. So why we got the contradiction? Because we assume that we suppose that V1 through Vr are linearly dependent. So V1 through Vr must be linearly independent. Okay. Yeah. So now, next one. Back to the introduction in 5.1, we saw the problem of the extinction of all. The question was the what? Let me write it down. Give me a second. Remember the introduction here, jk plus 1, and then sk plus 1, and then ak plus 1. This represent the number of the all in a juvenile and then sub-adult and then adult, right? In k plus 1th year can be modeled by 0 and 0 and 0.33 and then 0.18 and 0 and 0 and 0 and 0.71 and 0.71 and then 0.94 and then jk and then sk and ak. Let me simplify this one as this. Let's say this is the x sub k plus 1. And then let's say this vector is matrix A. Let's say this is xk. Okay. Right. Here. Then if we can find out the eigenvalue and eigenvectors, I mean, if this k bar is eigenvector, then it should, assuming that, then we can express this one as lambda k and then x bar, isn't it? Lambda k is eigenvalue corresponding to x bar, x sub k bar. Okay, right. But uh now then think about this x1. Let's find the x1. This is going to be a times x. Let's figure out now we see. I want to find out the pattern to find out to express lambda k in terms of the preceding eigenvalues and eigenvectors. So x1 is a times x 0. This is equal to lambda 0 and then x 0. Then x2 is going to be a times x1. This is equal to lambda 1, right? Times x1. But before doing that, give me a second. Lambda 1, x1. X1 bar, I mean, give me a second. So as long as the AXK bar is equal to lambda is times XK bar for any choice, any index K under that assumption, then we can derive XK plus 1 bar as lambda to the K plus 1 bar times X0 bar. Okay. Because XK plus 1 bar is equal to AXK bar, but this is equal to lambda XK bar, right? And then starting from k equals 1, we got this. Then k equals 2 is this. But we could express x1 bar as lambda times x bar, x0. So replacing the x1 with a lambda times x0, then we got this. Okay, and so on. Okay. That's for 5.1.